While he's opening my file, I wish to thank Rajesh and Abhishek and also the other organizers for giving me a chance here to talk about how quantum physics has affected. So let me get started. There are three parts in my talk today. The first one is really for general audience, an introduction, but I'll motivate that. The second is to celebrate the power and success of quantum methods in the context of material science. And third is new experimental spectroscopy, which we propose based on Berry curvature, which is like a new kind of a Raman effect, but which originates from Berry curvature. Yeah, that's the plan. So if you look at the website of this international area for quantum mechanics and technology, three of the mandates here, by the way, the mission says to help raise public awareness of the importance and impact of quantum science and applications in all aspects of life. And I'm going to show you that at least three of them, if not this, involve materials. So the impact of quantum mechanics through materials on civilization has been spectacular. Material science is a very exciting branch of interdisciplinary science. And it basically, the fundamental theme is how history of a material, starting from its processing, influences its structure and hence the properties and performance. It has this fundamental tetrahedral paradigm where the kinetics determines processing of a material, which determines structure, and structure determines properties. Properties determine performance, which is relevant to applications, and characterization, which of course involves theory and experiment hand in hand, is very crucial too. Quantum physics has addressed only this branch of the tetrahedron, okay, this side of the tetrahedron, and of course some aspects of characterization. And the way it is accomplished is basically amazing, and that's my first few introductory slides. It's a truly interdisciplinary and exciting science which affects society. So first principles theory based on quantum physics of materials basically involves how atoms interact with each other via electrons. And there, the fundamental idea is of the total energy function. Again, I'm skipping lots of details here, but this is the spirit of these methods. It basically uses atomic numbers and atomic positions. This function, total energy function, is a function of these two variables. Atomic numbers capture the chemistry of a material, and atomic positions capture the structure of a material. And this total energy has two parts. One is the many body minimum energy or ground state energy of quantum set of electrons, and the second is just electrostatic interactions between positively charged nuclei. And this is the part which is very hard to determine, as all of you here are aware of, and that is tackled typically using the framework of density functional theory, which was developed by Walter Kohn in 1964, where the essential idea is you don't have to follow motion of individual particle to determine ground state of many electron system, but you can work with average density of electrons and get, in principle, an exact answer about the ground state. And for which Walter received Nobel Prize in Chemistry in '98. This total energy defines the interatomic interaction, which of course is relevant to zero temperature properties, and you can use it within the StatMech as a Hamiltonian to determine thermodynamic behavior of a material. So these first principles quantum simulations were also called as the standard model of materials, quote unquote, by Marvin Cohen. And what do we obtain from that? If you minimize the total energy, you get three levels of structure of a material: the geometric structure, the dynamical structure, which is basically the vibrational spectrum, and also the electronic structure. And derivatives of this total energy function give you properties. So it gives you very natural framework to connect structure and properties, which is one of the fundamental ideas in material science. Of course, DFT came up in 1964, and lots of things are happening beyond what Walter Kohn developed. The first one is, of course, I declare that this doesn't work so well for correlated electron systems, and there are efforts to extend that reach to DMFT and similar ideas. The density functional theory also wasn't, but it's a ground state theory, so it doesn't give you electronic excitations accurately. So there are extensions through self-interaction corrections and hybrid functionals to access electronic excitations accurately. ironically, DFT also didn't capture weak interactions accurately, like hydrogen or van der Waals type interactions, and that has been surmounted in the recent years. There are more accurate functionals now, which all can feed into this motivated by thermodynamics. One can either do ab initio molecular dynamics or Monte Carlo to derive thermodynamic behavior, or the approach what I take in my group is basically to derive simple realistic models which capture the low energy physics of a material. And this has had huge impact on material research. Really, quantum physics through density functional theory has revolutionized how we design materials and research about them. So you'll see that through my examples. So of course, this is another mandate of the International Year. I should point out that there are lots of problems today, challenging problems human society faces, particularly in the context of energy and environment, where these techniques, which I just introduced to you, are very relevant, and particularly the problem of clean energy and environment, where you want to get rid of fossil fuels and replace them with renewable energy, which involve lots of processes, but at fundamental level, it just involves how electromagnetic fields and atoms and surfaces interact with each other. And this is basically the idea. So solar energy, for example, can be converted photocatalytically to green hydrogen, or to electricity to photovoltaic route and back, recycle back, and fuel cells can convert hydrogen to electricity. And to slow down global warming, you want to reduce carbon dioxide to useful hydrocarbons, which can again be recycled into engines. Yeah? So all of these ideas, the numbers here indicate each place has an open challenge of finding a new material which will do a trick, perform well as scale up well in technological applications. And there, indeed, the materials are key, and DFT is playing a very important role. It's being actively used by chemists, but that's not what I will talk about in the rest of the talk. I'll switch to more sort of physics-themed aspects of quantum materials. So the first point I'll make is phase transitions, in particular structural phase transitions in crystals, and how we can simulate them using first principles simulations. A simple example I can offer is a ferroelectric material, which is a very important technological material, which takes a cubic structure at high temperature, and as you cool it down, it breaks inversion symmetry to form a tetragonal structure, which is accompanied by a dipole moment associated with the positive titanium atom off-centering along z-axis, so ionic dipole moment. And once you break this inversion symmetry, new properties emerge, which are like linear piezoelectric response and nonlinear hysteresis, as shown here, polarization versus electric field. And these emergent properties are only in the low temperature phase, make it useful in sensors, actuators, speakers, and microphones in your mobile phones, and a variety of applications from heartbeat monitors to naval submarines. Yeah? So near the phase transition, these response properties are colossal in magnitude, and the instability of titanium off-centering is very important to these transitions. It's a phonon-driven transition because you will see the instability basically involves oscillations of the titanium atom with respect to the oxygen sublattice. Now, this relates to a very interesting simple concept called soft modes, which again has a history in Bangalore. Raman had discovered soft modes in silica structural phase transitions in 1940, along with Nedungudi. So if the crystal instability is determined by whether the vibrational frequency, which is the second derivative of energy with respect to vibrational amplitude, is positive or negative. If it's negative, it's an unstable vibrational mode. And in a structural phase transition, it's the high symmetry phase, which is stable only at high temperatures, is unstable. And if you extrapolate the frequency down, this is where the phonon becomes soft, as observed by Raman, and later also introduced by Cochrane and Anderson. And this unstable mode defines the instability of the high symmetry phase. And that is what governs temperature-dependent structural transition. And this kind of instability is not so easy to determine experimentally because you don't have access to high temperature phase at 0 Kelvin. And that's where DFT calculations or first principles calculations are very valuable. They give you access to materials instabilities, whether they are structural transitions, structural instabilities, or magnetic, or other types of instabilities. Of course, there are scientific challenges in this endeavor, in the theory of structural transition. First of all, you need first principles theory because we want to predict transitions which are material specific and hence can really relate to a specific application. They involve small total energy differences, typically of a tenth of a milli eV, whereas the energies are of thousands of eV. Secondly, these are temperature dependent structural transitions, which means you can't work with simple harmonic picture of vibrations. You have to have nonlinear phonon interactions. And of course, that means you need to use MD or Monte Carlo. And third, phase transitions occur strictly in infinite size limit, and which means Monte Carlo MC simulations will be very large, and ab initio MD are computationally too expensive to do that. Okay, so this is what is the another limitation of quantum simulations. They are computationally quite expensive. The CPU time scales with order n cube, where n is the number of atoms or electrons, and the memory size scales as order n squared. So to do this, use this directly for simulations of structural transitions is often difficult. So what we do is, as since material, many other problems also involve multi-scale behavior, we use modeling strategy to bridge length scales and time scales. So the approach we take in my group is basically summarized here. You start from DFT calculations, which give you access to processes on the scale of few nanometers, or couple of nanometers. We do coarse-graining in time domain by integrating out the high energy degrees of freedom, in this case phonons, and get a model Hamiltonian, which is basically focused on unstable modes, and that can be used in molecular dynamics or Monte Carlo to predict phase transition material specific aspects, not the universal aspects of phase transition necessarily. Of course, universal aspects are also available to us, but our focus is on material specific aspect. Then we do coarse-graining in real space domain, and there we develop some of the tools our own. Like thermostat, we have a polostat, and that allows us to get Ginzburg-Landau type theory, essentially from first principles. And once you have this theory, you can access length scales which are much longer, hundreds of nanometer, and that allows us basically not only fundamental understanding of these phase transitions, but also simulations of devices. So this is what comes out of this first principles calculation. This is phonon dispersion of barium titanate and lead titanate, and these phonon modes, frequencies are on the y-axis. The ones with negative, which are basically the imaginary vibrational modes, determine the structural instabilities of these two crystals. And you can clearly see that they are quite different in terms of their behavior. In lead titanate, you have unstable modes everywhere in the Brillouin zone, whereas in barium titanate, they stabilize in some parts of the Brillouin zone. So basically, our focus is on these unstable modes. So effective Hamiltonian we work with is a projection of full lattice Hamiltonian into the subspace defined by this. And how we do this projection is another technicality, but we use basically phonon one-year functions to that projection, which basically assume simple interactions between higher energy and low energy phonons. Using this approach, we can predict phase transitions. Now you see the success of this theory. Basically, we have used a recently developed DFT functional by John Purdue. This is called strongly constrained, appropriately normed DFT functional, which satisfied 16 different sum rules, and which is known to be more accurate than the earlier flavors that we used, which grossly underestimated the transition temperatures. But with this, some of the new advances in DFT, now we can predict TCs even with this modeling within 10% of the experimental TCs. And not only that, you see the contrast between lead titanate and barium titanate. Here you have 3 phase transitions. By the way, the 2 sets of lines are associated with heating and cooling simulation. These are all first order phase transitions. Associated with that is the hysteresis. So this is really truly remarkable success, I feel, of a quantum-based approach to predict these transitions with reasonable accuracy. So instabilities are important ingredients we access using DFT. Now I'm going to give you a very spectacular example of a material. Based on that, futuristic memory devices are proposed, and this is hafnium oxide. It's an oxide which is already used in silicon industry, so it's very easy to incorporate in a sort of ongoing silicon-based semiconductor technology. This takes a calcium fluoride-like structure, which is shown here. This is hafnium is on an FCC lattice, and oxygens are on the cubic lattice with half the lattice constant. And what we find is the only instability in hafnia, cubic hafnia, involves actually antipolar displacements of these oxygen chains. And these, of course, you will not give you electric dipole moment because half of the negative ions go one way and the other half go the opposite way. But they couple beautifully with these two phonon modes. This is the polar modes, which is this, and this is antipolar modes, and this is here. And you will see they condense in the low temperature phase with equal amplitude. And if you add up these two phonons, you will get zero dipole moment in one spacer layer and a large dipole moment in another layer. Okay, so this is basically a sheet of oxygen atoms which get dipolarly polarized. Yeah, so this is remarkable. You have alternating two-dimensional spacer and ferrodipolar sheets in this hafnium oxide. It's an anionic ferroelectricity, unlike the perovskites where it's driven by transition metal. Second very remarkable aspect of this ferroelectricity is even if you switch one dipolar sheet in the opposite direction dipole of that, basically you get the energy which is very comparable to the ground state. So you have an infinitely degenerate ground state which is associated with any ordering of these dipolar directions of these two-dimensional sheets. Yeah, this is contrasted with the conventional ferroelectric lead titanate, where if you try to switch one one sheet of titanium atoms, you will see it basically leads to increase in the domain size and overall switching of the full sample. Yeah, so the advantage of hafnium oxide is you can store memory in single dipolar sheet shown here, which has about the same energy as the starting point. So you have 2 bits per nanometer possible in terms of memory storage, and that's really remarkable. In fact, the limitation on the density of memory will be determined by how small electrodes you can deposit on it, and the material. Second advantage is it's a 3-dimensional crystal architecture. It doesn't require experimentalists to grow it in a nanoscale or fabricate in a nanoscale. You have a bulk film and you can make use of it just by patterning the electrodes on it. So these are ultimately high density storage devices possible, and this was the work we published in 2020. And later, basically, what we have shown is there is phonon pairing in this material. The physics of this ferroelectricity is very fascinating. These two phonon, polar and antipolar phonons, are coupled by this zone boundary phonon vibrational mode. And once they couple, you get basically this pattern. And there are 3 pairs of phonons at least which are involved in this phase transition, which means there are 7 component order parameters, but they're very special because they involve pairing of phonons, like pairing of Cooper pairs in some sense. In this case, the mediated interaction is by another phonon. And as a result, what we have shown in detail is the domain wall in this material, which separates up and down dipolar polarization, is identical in structure to its bulk. You know, that bulk and domain wall are more or less structurally similar. Yeah, and there is an experimental proof now we find from the Korean group where they have measured atomic positions using very high resolution microscopy, and they verify basically this prediction we have that domain walls are identical to the bulk, like boundary and bulk are identical. Yeah. Okay, so I will now switch gears and move to coupled quantum classical degrees of freedom. And this is designing crystals with broken symmetries. The dipole moment I talked about was essentially based on charges. Now we will have spins come in with us, and that makes things much more interesting. So the perovskite oxides, these are AbO3 oxides, where B atom is typically the transition metal, are very fascinating because they show different types of symmetry lowering mechanisms which give rise to emergence of diversity in their properties. Now, ferroelectrics are typically characterized by transition metal with D occupied with no electrons. That's boring to many of you because that means it will have no magnetism. Whereas if you want to have magnetism, you need Dn not equal to 0, which gives a spin. And they're typically metals. These are insulators, and these are polars, and metals are typically centrosymmetric. They're non-polar. And in fact, now we will be introducing a class of metals we call unusual metals, not strange metals. In the sense, these are non-centrosymmetric metals. But even more interestingly, we find we want to combine them. We make half metals, meaning it's metallic in one spin channel, and it's gapped in the other spin channel. So one spin channel favors ferromagnetic itinerant electrons, and the other spin channel has bound electrons which support ferroelectric polarization. And they are also coupled with each other in a beautiful way. Yeah, so how do we do that? And this is another sort of aspect of this new type of methodology where it gives you a very unbiased tool to explore new material structures. Yeah? So we start with a material which has not well understood experimentally. This is lead manganese oxide, and first we established within the accuracy of our methods that it's a ferromagnetic half metal, and we want to make it polar. So we start with something which is interesting, we want to make it polar. There are many possibilities, but we find out that there is usually a competition between rotational modes. Rotations means the MnO6 octahedra rotate out of phase here or in phase, versus the dipolar moment, which is the polar phonon at gamma point. And this competition stops this from becoming polar at any cost. Yeah? So we tried 3 different routes to make it polar. One was to try epitaxial strain, where experimentalists can grow these films on a substrate and engineer the in-plane lattice constant. Second was basically cation substitution. You can substitute manganese with other transition metals, or you can substitute use heterostructuring. What Manda talked was van der Waals heterostructure. This is epitaxial heterostructure possible, where A and A prime atoms are different in the adjacent layers. So what we succeeded in doing is we predicted a heterostructure, or some people call it superlattice, of lead manganite and strontium manganite. See, the top layer is lead manganite, followed by strontium manganite. If some of you are critical how you will make it, it's possible to make this in the lab fairly well. In India, and some of our colleagues are a bit reluctant because MBE, what they use for this molecular beam epitaxy, gets contaminated if you use different elements, particularly lead. So we're going to see if this can be made. So there is a lot of symmetry analysis which goes into it, and then detailed calculations. I won't go into those details, but what we have shown is this superlattice has a space group which is polar, and it is half metallic ferromagnet. This is the electronic structure of it. You see the downspin electrons have a gap, the red bands, and the upspin electrons are metallic. So the picture of this material is very fascinating. You have a macroscopic dipole moment, like a ferroelectric, which in principle is switchable. But you also have because it's metallic in the opposite spin channel, those free carriers will screen this dipole moment, and those are shown by here. So you will develop an opposite dipole moment, possibly a little different from this, if there's imperfect screening. So you have 2 dipoles which are spin polarized, macroscopic electric dipoles which are spin polarized. So in some sense, just like you have in spin dependent current, here you can have spin dependent displacement current, but you will have a displacive current here and resistive current which sort of is oppositely spin polarized, which opens up, of course, lots of applications. And we are now following it up basically to look at the domains in these systems and examining their behavior, and also bringing in quantum geometric features into multiferroics like this, which will bring in yet another dimension to multiferroicity. If Berry curvature dipole is an order parameter, that will be yet another way to develop multiferroics. The last part of my talk, I have about 10 minutes, is about the new class of spectroscopies we have proposed based on this theory and the physics of Berry curvature. So the first part of it will have strong overlap with the pedagogy Mandar had, but maybe from a slightly different angle, it may make it clear to some of the students, at least in the audience. Okay, so this is a proposal using first principles theory of a new class of spectroscopies which are based on quantum geometry. And we demonstrate it here in the context of vibrational spectroscopy of 2D materials. This is like a new type of Raman effect. And in fact, the last year was 100th year of first measurement of Raman effect. And we are really pleased that we are coming up with this new prediction, which gives you sort of combines ideas of Berry phases and the Raman effect in one. So the background to this, some of this Mandar talked about, is in a crystal, wave vector K is the quantum number of electrons. It's a continuous vector, and it belongs to a single unit cell, or what is called as Brillouin zone in K space. And since this is, these are the semi-classical motions of equation, basically if you apply electric field to this electron, acceleration is created, which is given by derivative of K. So K is like a block momentum of a crystal. So when you apply external fields, electrons basically traverse trajectory in the K space in this Brillouin zone. Now this Brillouin zone is also periodic. The electronic structure is periodic in K space as well. So you have a toroid, torus picture like this for 2D Brillouin zone. And what it means is electrons can going across one end of the Brillouin zone to another basically is a closed path. So you can calculate Berry phase, or what you will see is Pancharatnam Zach or Berry phase. Pancharatnam again comes from Bangalore. And what has been shown is for block electrons, if you calculate this phase in the K space from one end of the Brillouin zone to another end of the Brillouin zone, it gives you average position of an electron in that band. Alpha is Cartesian index, x, y, z. And this is the key. In fact, this is the key to understand what Mandar talked about. I will explain how the transverse velocity arises in a 2D case. So in two-dimensional case, the Berry phase and Berry connection will also lead to us calculate Berry curvature, which is the case curl of Berry connection. And gamma alpha are basically the Berry phases which give you average x and y coordinates of an electron. So if the trajectory of if omega is non-zero, and if the electron is moving along this blue line, you will see it goes from one kx to kx plus delta x. It can lead to change in the Berry curvature in the y direction if omega is non-zero. And now you will realize that if gamma y changes as a function of kx, which means the Berry curvature is non-zero, it means the electron drifts along y direction because that's the average y position of an electron. And that's what gives rise to a Hall effect even in the absence of magnetic field. This is a simple way to understand the origin of anomalous Hall effect. It's anomalous because there's no magnetic field, and the shift arises from the fact that average position of electron along y direction changes as the electron moves from kx to kx plus delta x. Yeah, so that's the idea. Then it has been shown long ago that if you have a two-dimensional metal and if you calculate the Berry phase like this along a Fermi loop, a closed loop, you get basically phi, and the off-diagonal conductivity or Hall conductivity is essentially this quantum times phi. And that means if you apply electric field along x direction, it will create a current along y direction, and that's the anomalous Hall effect. To summarize these basic ideas, the correspondence between the emergent fields and the geometric band theory, you have Arano-Baum phase in this case, which is similar to Pancharatnam-Berry phase. Berry connection is like the vector potential, curvature is like a magnetic field strength, and the Chern number is basically related to the Dirac's monopole charge associated with a band crossing possibly. Yeah, unfortunately, symmetries are highly restrictive. If a system has time reversal symmetry and inversion symmetry, you will see the Berry curvature satisfies this condition for spinless electrons, and as a result, Berry curvature is identically zero in such systems. For most systems like silicon, aluminum, this is not going to be really relevant. So that's where the nonlinear Hall effect becomes very useful, as Mandar talked about it. The nonlinear Hall effect basically relies on the fact that when you apply electric field along x direction, it creates an asymmetry in the Fermi surface due to shift in the K space along x direction, and that basically can give rise to effects which are related to the first moment of this Berry curvature, and that's what was shown by Liang Fu and Inte, that the Berry curvature dipole, which is defined by this as shown by Mandar, gives you anomalous nonlinear Hall effect Jy, which is quadratically dependent on the electric field Ex, and the proportionality constant is given by the Berry curvature dipole. Yeah. And that's basically the key thing in the spectroscopy that we are going to propose. Now, the experimental verification of nonlinear Hall effect came up in 2019 by Pablo Herrero's group. Basically, anomalous Hall effect gives rise to electric current, transverse electric current at the same frequency, so overall current has an angle with respect to the incident angle, whereas in the nonlinear Hall effect, the effect is very clean, although it is weak because it's a nonlinear effect. For a field along x direction, the Hall current at double the frequency or zero frequency, which is rectification, is always perpendicular to the applied field. So which is a very nice thing in terms of measurement convenience to have in terms of experimental measurement. So Bhuvaneshwari, which Mandar also referred to in his talk, we calculated the Berry curvature dipole of the non-centrosymmetric tungsten telluride and find that this is the Berry curvature distribution in the Brillouin zone, and it has a dipole moment because there's only one mirror reflection symmetry in the lattice. And basically, this is to sort of get started. You need to have low symmetry to have non-zero Berry curvature dipole. Now we said, well, crystal symmetry can be lowered dynamically. Right? Mandar, in his last part, proposed that you modulate Berry curvature dipole by applying time-dependent strain. We say, well, the same can be done in a natural way if you have a normal mode in the system, right? If it couples with Berry curvature of the material. And that's what we capitalize on. So you have a basic idea here that you have this graphene-like system or any lattice. Vibration will lower its symmetry dynamically, and this dynamically lower state can have Berry curvature dipole, which is non-zero, and vibration can create oscillations in nonlinear the Berry curvature dipole, and hence the nonlinear Hall effect. And that's based on that, we propose the spectroscopy called geometry of quantum electronic structure based spectroscopy. So the idea is this: you have this Berry curvature dipole as a function of time. It has the same period as the vibrational frequency, and the vibrational mode is GQUES active if the derivative of dipole moment with respect to amplitude of vibration is non-zero, similar to IR active mode. In IR active, you use the electric dipole of the lattice. Here is we use Berry curvature dipole of the crystal. So based on that, one can show the response of transverse current basically is proportional to Ex squared. The first two terms Mandar talked about are the nonlinear Hall effect gives zero frequency and second harmonic generation. But this part is new, which basically says there will be additional modulation which are linked to the vibrational frequency plus minus 2 times the applied frequency, and also the peak at omega 0, which is associated with the rectification part of the nonlinear response. So GQUES can be done in transport spectroscopic mode. So transport meaning you just have a simple 4 electrode device like this, apply electric field with a frequency omega, and measure a Hall current as a function of frequency. You will see there are 3 peaks we predict using this spectroscopy. One is associated with the vibrational mode, which is like an IR active mode. And this is, by the way, when you have no Berry curvature dipole to start with in the system. So symmetry of the lattice is not so crucial to be equilibrium symmetry is so crucial to this. And you have Stokes and anti-Stokes like modes. But remember the contrast in Raman, the Stokes and anti-Stokes are adjoining the frequency of light. Here, Stokes and anti-Stokes are separated by 2 times the frequency of applied voltage, and it's centered on the vibrational frequency of the phonon mode. Yeah. So you can also have another mode called emission spectroscopy, which basically means using terahertz frequencies. You shine a terahertz frequency light, which is commercially available in the world, and basically measure radiation emitted by this device with a field which is perpendicularly polarized as a function of frequency. You basically get again set of peaks, which is shown here. One is related to the rectification. You have 2 peaks associated with rectification. One is at 0 and one is at 2 times omega L if the Berry curvature dipole is non-zero. And other 3 peaks basically are linked to Stokes and anti-Stokes as indicated here, and the mode at phonon frequency itself. Yeah. Wonderful. So this is basically what our predictions are. We demonstrated this with specific predictions for materials that are available in the lab today, and I won't, given the limitation of time, I'll quickly go through it. So first we worked out for non-centrosymmetric tungsten telluride, and we predict that Berry curvature dipole moment is linearly proportional to strain, and that's what will give rise to the spectrum which is shown here. If you change the applied AC frequency, the Stokes and anti-Stokes peaks move around. So there is an additional control over the spectra here. By changing the driving frequency, you can monitor the Stokes and anti-Stokes peak and then confirm the vibrational frequency. The second advantage here is basically this is for, okay, let me skip this part. Yeah. So you have a possibility to transduce signal from gigahertz to terahertz. The vibrational mode that Mandar talked about may be in gigahertz, and you may apply electrical voltage in gigahertz frequency. But if your radiation is emitted in terahertz due to the phonon frequency, you can see the modulations in terahertz regime. So it opens up yet another technological application in addition to having a vibrational spectroscopy. So at this stage, some of you will be quite critical. This is applicable only to the materials with non-trivial quantum geometry, and there are not too many materials with such properties. Well, we overcome this limitation by learning from surface enhanced Raman scattering, where we use a substrate of quantum geometrically active material like graphene that Mandar talked about, and then measure frequencies of something like boron nitride. Boron nitride is a boring insulator which has a large band gap and no Berry curvature, which is non-trivial. But if you deposit it on graphene, its vibration can induce oscillations in the Berry curvature dipole of graphene, and that can be measured, and we have calculated it from first principles, and we predict this is the spectrum that one should see for HBN on deposited on graphene. So this really expands the applications of quantum geometry-based spectroscopy to wide variety of materials. In fact, it's an application of a quantum material like graphene in measuring vibrations of other systems which may be rather sensitive. Okay, I will skip all of this now. The spectrum is very rich for the even centrosymmetric tungsten telluride, and it's very easy to understand. Whatever we did so far was semi-classical. One can also develop quantum mechanical picture of this, which is very similar to Raman. I'll just give one take-home message here that in Raman spectroscopy, you rely on the real part of AC dielectric constant and its modulation with vibration. Here we are relying on the off-diagonal conductivity, which is the imaginary part, and in particular dependent on Berry curvature dipole in developing the spectroscopy. So it's very nice coincidence that we came up with this idea in the 100th year of Raman, and we hope this will open up lots of possibilities for further research. Mandar already has some indications. He's doing these experiments to verify our claims, and I acknowledge my student Bhuvaneshwari, who came up with the idea of this GQUES spectroscopy, and other collaborators, in particularly Mandar, who is here, who kept us on the right track to be close to experimental ideas. Thank you.
Questions?
Maybe a naive question, but is the symmetry lowering that you described a materials version of the Jahn-Teller effect in molecules? Is there a connection?
Okay.
It smells, it's a similar smell.
Well, yeah, very interesting point. So the oscillations in Berry curvature, which are induced by vibration, have a flavor like that. Okay, basically, if you look at the Berry curvature formula, you have a band gap which is in the denominator, and if that gets modulated, I showed a band structure rather quickly, how the band energies oscillate, and that generates the oscillation in this. Yeah. So I won't say it is Jahn-Teller strictly, because Jahn-Teller has some other flavors which are not necessary here. For example, graphene electronic structure, which is a Dirac point, or if you have a Weil point, that is adequate to do this, because the vibration will lower the symmetry, open up a gap, and create oscillations in Berry curvature in the neighborhood of Weil point. Yeah.
Center.
Yeah, thanks, Umesh. Very nice. By focusing on the nonlinear Hall effect, that's just affected by the Berry curvature dipole and things like that. Now, if instead you also look at the longitudinal nonlinear transport, would that not get a contribution from the from the real part of the quantum geometry tensor, the quantum metric itself?
Yeah. So. Okay, real part of Berry curvature-like object, as Mandar defined, is the metric.
Yeah.
Which actually is just localization length squared in my view. Yeah. So if you're right that can also be sensitive to gap, it's inversely proportional to the gap, and should have. It's a very good point. We haven't really thought about it, but we calculated that object in 2003 in very different context, where we wanted to study vicinity to a metallic state.
Mm-hmm.
Yeah. So that may be interesting to consider. Yeah. Thank you.
Abhishek.
Yeah, Umesh. Yeah.
Yes.
So normally, if you are looking at Chern insulator, and if you're looking, like, you can relate the Hall conductance to the journey invariant using the green Kubo and TKNN formula, right?
Mm-hmm.
But here, when you're looking at the nonlinear response, I mean, you don't have a green Kubo, I guess. So how do you show this relation to the?
Okay, there I would basically remind that when you apply electric field, you create asymmetry in the population of electrons in K-space in the neighborhood of Fermi surface, right? So we still use the same anomalous Hall effect, but it's second order because the population itself depends on the electric field.
Okay,
So
so
it's
you're still doing
nonlinear,
linear
yes.
response.
Yes, well, it's, yeah, Boltzmann transport where electric field induces the Berry curvature. Yeah.
Yes, sir. Here,
Umesh?
thank you for nice talk here. Actually,
Thank you.
actually, in class we teach that Raman lines are the characteristic of the material, not the applied frequency of the applied source. But here you are saying that the Raman lines are changing with frequency of the source.
No, I did. So these are not Raman lines.
Okay.
I contrasted that. In fact, this is more useful than Raman in the following sense. By changing driving frequency, you can change the Stokes anti-Stokes line. Average of that will give you the vibrational frequency. See, here the idea is to measure vibrational frequency. Whether you measure Stokes or anti-Stokes, finally your goal is the vibrational mode. And that comes out in a sort of, more controlled manner here than Raman. In Raman, to assign modes is always a challenge, for example.
Yes.
Yeah.
Okay, thank you.
Umesh, can the Berry curvature dipole fluctuations lead to a displacive transition?
Very interesting question. I don't really have an answer. Berry curvature dipolar fluctuations give structural transitions. I see. The other way, yeah. That relates to the Yan-Taylor type ideas, where Yan-Taylor drives the symmetry breaking structural distortion, and there also the Berry curvature will open up. Yeah, so indeed, this is an interesting question. I don't have a concrete answer, but it has similarity to what Michael asked. Yeah. Okay.
Other questions? If not, let's thank Umesh again and
Thank
both
you.
speakers.